Alright, boys. I'm super late to the party, but day 18. Let's go. So, events of code. We will see what happens. You go the interior. So, what in the frick is this? Off the ground, take specified numbers meter up, down, left to right. Oh, wait, why would it be colored? I guess the colors are for the second part? So, I guess I just do a graph traversal again. Okay. I don't know. I'll just do like. Well, okay. So I have to. It doesn't mention any use of a color yet. Okay, let's see how big the input is. It's not that big. So what I could do is I can run through the instruction once and figure out the size of the entire grid. I guess I'll do hash map of. So if it's right, I'll do what? Okay, so 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, I see. So if it's right, then I do. And I could just do 0, 2, 1. So if it's down, just do 1, 2, 0. Then this is -1. I have to look up directions. And I guess I'll figure out the information. Yeah, so I can just do, I can split it by a space. It should be fine. So, yeah, do this. There we go. So now I have the size of the grid. I have array of, hmm, there we go. Wait, I just realized. What am I doing? Why am I naively creating a graph? I just need to find the size, and then I need to. I'll do so n times m minus. Yeah, there we go. So that's my input, and so 32. Oh, because crap. Yeah, this doesn't even work that good, anyways. Oh wait, this is supposed to be. Let me make sure this doesn't crash. It doesn't. Good. So now, going to fill in the outside. I need to change this as a int array. Hmm. Okay, now we finally have our answer. This took a while. One. Okay. I'm gonna make this work. I just realized. and and what if I also If I'm just extremely lazy, instead of trying to make the negatives work, mm, I mean, I already suspected in the beginning that this was going to happen, but I thought I didn't have to worry about it. I thought offensive code would be nice to make it so you always, at the least, you end up at a starting point, not go in the negatives territory. So, or actually, I can make this work. I can make it work. So n is equal to max n plus negative min n plus 1. And then we do same thing for m. I don't care about name shadowing. I don't care. Does it run for the example input though? I guess I'll try running a debugger on the real input, see what the variables are. Hmm. Okay. Actually, yeah, this should be fine. So this is fine. It's just this. Because this graph traversal just I'll be right back, boys. Okie dokie. Isn't it supposed to be plus 2? My answer is too high. Yeah, I suspected this might not be fully correct. 63, what? Did we get 63? If I do this, it's 60. Oh, oh, alright, guys. 3 days later, I gave up on part 2. I'll admit, I give up. I give up. Now, you might be asking me, what made you give up? Well, in order to solve the second part, which I knew it had to be, geometry, because, like, if you just decode all the instructions out, like, each individual move, they move insane amount. Like, look at this. So look at this answer. You're telling me that I'll just naively get this answer? No, there's no way. So what is it that you need to know to solve this part 2? Well, there's a thing called I did not know this, by the way, both of these. So one of them is Higgs theorem. So basically, it relates the area of any lattice polygon. This is important. This is called a lattice polygon. I've spent like all day researching this crap, so you guys don't have to. So lattice polygons, they are when they're so when you have a polygon, right? Polygon consists of vertices that mark like the corner points essentially, and then you just connect them. And that's what our input is. But if you visualize your input, you'll see that it's like if you make it start at a certain coordinate, after all these moves, it'll go back to the same coordinate. So you've essentially sketched out a polygon while you're moving. And it's also a really nice polygon because it doesn't have these slopes. It's just either horizontal or vertical lines. So this image will come in a sec. So Pick's theorem. And another thing you have to know is called a shoelace theorem. These are really close related, and I'll explain one confusing thing to you. So the shoelace theorem allows you to find the area of a polygon. You have n points. So this is a formula we definitely want to use because we don't know how many points we have, but we know it's a lot. Like, look at this. Every single time we turn, we basically create a point. And we have all this. So this is what I did in Kotlin. So I scanned every line, right? And then I parse the last little bit of each line. I remove these surrounding things. So I'm only working with the third character, third string in the line. I manually decode out how many units to move in that direction. I get a direction itself. And now I'm just updating my current X and current Y. So there's two things you have to keep track of to execute the shoelace formula. One, the points. So you want to store them as an array. And want to make sure that they're ordered. So it's not like you have first index, you have this point, right? And then you have this point, and you have this point. It should be like first index, this, or you can go counterclockwise. Now, if you want to learn how shoelace theorem works, they're just exploring this thing called cross product, which I don't know yet, but I don't know what cross product is. But I guess it has a really nice property that allows you to cancel out extra areas. So that's how they made it work. But yeah, you do this. So this is what I'm doing, zip with next. So I go through each pair of consecutive points and I just run this thing. So this is the interior area. Okay, now this is where the confusing bit begins. You might notice that Shoelace theorem gives you an area, but Pick's theorem also gives you an area. So why are we using two different things when they both give you the area? Well, our input is not exactly correct. You can't just dump it into Shoelace formula and expect to get the right answer. That's where this diagram comes in. So if you imagine literally, you have an entire grid. You have a Cartesian plane, right? And you just sketched out the points. Like see, you just sketch out these corners, right? So let's say you go here, right, and go 2 down. So what does that look like? Well, if you look at this, maybe I should just do this so that I can kind of demonstrate what I'm talking about in a more visual way. So if you start here, right? Remember, this is what Shoelace expects. You start at the corner of these little squares in your grid. So you go 2 over, right? So you go 1, 2. Well, what's the problem? Well, this is width 2. But in the context of events of code, this is actually width of 3 because this starting point has a width itself, if you know what I mean. So this is why it's called lattice. Crap. So what we have to do is we have to mark this as 0, 0. Right? This is 0, 0. And when we want to move 3 units over, we do 1, 2, 3. So this is 3. This is vastly different from if you started here and 1, 2. Wait, what the frick? Oops. If I do 2 over, sorry guys. So 1, 2. Now this is with 3. By making it so that we start at the center of these little grid things, we made it 3 in width instead of being 2. Let me just draw up here so that you guys can compare in your heads. Remember, when we're calculating the width, we're calculating how much of entirety of these blocks are we including. So the cool little thing about bottom here, right, is this is, so it technically still including only 2 blocks because this is a half of this right here. This, you can imagine, this is half width and this is half width down here, and then we have 1 full width here. So we get 2 from here, and now we consider this half width. So that's another 1. So that's why we have 3 here. 3 for the width. Okay, now I'm slowly getting to the juicy bit. So shoelace allows us to find the area inside this rectangle. So like this area. Now remember, this is technically 2x2 square. It's not 3 times 3 still. But we've placed the points in the center of these grid squares so that we know how to fix this answer. We have to fix this. So this gives us 4. Right. But we want to include these outer squares, right? Now what squares are we missing? Well, if I shift this entire square so that it lines up exactly with the grid, you can see we're missing 1, 2, 3, 4, 5 squares. So how do we add those back? Well, you can notice that when we have a border, so we have 8 border squares, right? We already keep track of our border in this. So you can think about it like, how do I even explain this? So notice that we have, I'll just use yellow. 4 of them having a leftover width of half. This is a half, and this is a half. This is a half, and this is a half. Well, what about these corners? So now, when we deal with these corners, these are, I'll use purple. So these corners are 3/4 of a full square. So we basically have, what the heck did I just do? So the areas we have now is basically, so 4 times a quarter, well, a half of a square, plus 4 times 3/4 of a square. If we plug that in, turns out it's 5, right? Right, so oh shoot. I'll just put it here. So now see, we get the number of missing cubes. We get the number of missing squares. So we have 4 from the shoelace, plus 5 for the missing squares. It's 9. Now it would be nice if we can like turn this into a more general form. So turns out, if we have borders, right? It it's borders divided by 2 plus 1. And the way you can imagine this is every uh oh boy. So if you take all the borders except these 4 corners and you pair them up together, you add up all the half they have. So you have borders. So essentially have this. So borders minus 4 divided by 2. So that's how many new squares you have. And then, well, we need 4 of them. So 4 times 3/4. If we simplify this down, so we have this plus 3. Because these 4's cancel out. And this is basically saying the amount of space you have on the outside of these 4 squares, when you add them together, they make 3 squares. Then, how do we turn from this to this? Well, if we think about the logic of pairing the squares again, so this is 3. So this is 3. And then, remember, this amount is fixed because we consider 4. Basically, every single polygon will have 4 of these pointy little squares that have corners pointing out. Like it always happens. So this fixed amount, we can turn them into, we can actually turn this into like another pair. How? Um, How do I even go on explain this? Hold on, let me think. Yes, okay. So from these four squares, you get two pairs, right? Two pairs. And let's pretend we have two pairs of half and then times two, which gives four. And then we'll have to adjust it so it's minus one. Wait, so it's plus one. Yeah, so with plus one, we do transformation from this to this. This is like a little trick. I'm not really sure to intuitively explain this. But then, once we have this, we can simplify some more. So this turns into 4 over 2. 4 over 2. And then we're able to move the 4 minus 4 here because when we add positive 4 and negative 4, they cancel out. And voila. So I guess essentially we look at these four last squares and since it's always four squares that have this condition, we can turn it into like value based on halves. When we have these 3/4 being applied 4 times, it's like one more than what you have if you apply half. So minus 4 times 1/2. So this is a difference. We just turn the value into this. So this is one more than this. So yeah, this is all we did. We just applied this transformation. So that will get us to have a 2 for the denominator of the fraction, which we can use to simplify this part. Yeah, I think the hardest thing was, for me at least, figuring out, okay, so shoelace gives us this area. Why isn't it already the answer? Because it's not. It's really not. Like the size of this rectangle, well, this square, I mean, it's not the same as the input. So, yeah, GG's boys. I made the few for this one.